Hi there, Miss Barber here. This lesson is titled Trees. Definition. A tree is a connected graph in which each edge is a bridge and has no circuits. All trees have the following properties. There is one and only one path joining any two vertices. Every edge is a bridge. A tree with n vertices has exactly n-1 edges. Graphs that are trees. Consider the graph on the left. Note, this graph has 7 vertices. The vertices are A, B, C, D, E, F, and G, and it also has exactly 6 edges. Every edge is a bridge, which leads us to any two vertices are connected by only one edge. That is, if you move an edge, then the graph becomes disconnected. Let's consider the graph on the right. This graph also has 7 vertices and 6 edges, and every edge is a bridge. That means any two vertices are connected by only one edge. Graphs that are not trees. Consider the graph on the left. The graph has 6 vertices, which means it should have 5 edges, but it has 6. Furthermore, this graph is one big circuit. Let's consider the graph on the right. Every edge is not a bridge. For example, BE, EG, GC, BC are not bridges. The graph has 8 vertices, should have exactly 7 edges, but has 8. The graph also contains a circuit. Consider BCGEB. Example. Determine which of the following graphs are trees. Justify your answer. We begin with figure A, which consists of vertices A, B, C, D, E, with one edge drawn from A to C. This graph is not a tree because 1, it is disconnected, and 2, a tree with 5 vertices must have 4 edges. This graph has only 1. Let's look at figure B. It consists of vertices B, A, C, D, E. This graph is a tree because 1, it is connected. 2, every edge is a bridge. And 3, it has one less number of edges than the number of vertices. We now consider figure C. Figure C is a graph with vertices A, B, C, D, E. The edges are A to B, A to C, A to D, D to C, and D to E. The graph is not a tree because 1, it has a circuit, ACDA. That's sufficient to say that the graph is not a tree, but let's go ahead and list another reason. 2, the number of edges must be exactly 1 less than the number of vertices. This graph has 5 vertices, therefore it should have 4 edges. However, the graph has 5 edges. Definitions. A subgraph is a set of vertices and edges selected from among those of the original graph. A spanning tree is a subgraph that contains all of a connected graph's vertices and contains no circuits. A spanning tree is constructed from another graph by removing the edges while still maintaining a path to each vertex. Constructing a spanning tree, we begin with a connected graph. The graph is connected because there is a path that connects any two vertices. We move to the right to a subgraph, but not quite a spanning tree. The subgraph is a subset of vertices and edges of the original graph. And finally, moving one more step to the right two different spanning trees. The spanning trees contain all of the vertices of the original graph and has no circuits. Example, find a spanning tree for given connected graph. Example, find a spanning tree for the given connected graph. This graph has 8 vertices, A, B, C, D, E, F, G, H, and 12 edges, A to B, B to H, H to G, G to A to C, B to D, H to F, G to E to C, C to D, D to F, F to E. A possible spanning tree must contain all 8 vertices of the connected graph. However, the spanning tree must have one less edge than it has vertices, so it must have 7 edges. The graph, however, has 12 edges. We need to remove 5. How do we decide? There is a little bit of trial and error involved. Let's begin with remove CE, then AB, then BH, then GH, and GE. Look what happens. Now we have a connected graph with no bridges and exactly 7 edges for our 8 vertices. Example, find a spanning tree for the given connected graph. A possible spanning tree must contain all 8 vertices of the connected graph. The spanning tree must also have one less edge than it has vertices, so it must have 7 edges. The graph, however, has 9 edges, so we need to remove 2 edges. The plan is to break circuits. One possible option is to remove the edge AF. That breaks the circuit AFEA, and remove the edge GH. That will break the circuit HGBCH. Then it'll give us the spanning tree with the right number of edges, that's 7, for the number of vertices, 8. Definition: a minimum cost spanning tree is the least expensive spanning tree of all spanning trees under consideration. For the weighted graph represented by figure A, figures B and C are 2 possible spanning trees. The spanning tree of figure B has the weight 15 plus 8 plus 24 plus 12. The weight of each of the edges, that's 59. The spanning tree of figure C has the weight 8 plus 20 plus 17 plus 12. The spanning tree of figure C has a smaller weight than a figure B. Is it the minimum spanning tree? Or do we need to continue to find all remaining spanning trees to determine if one may have a total weight less than 57? That's one option. Another is Kruskal's algorithm. We can directly construct the minimum cost spanning tree from a weighted graph. To do so, 1. Select the lowest cost edge on the graph. 2. Select the next lowest cost edge on the graph that does not form a circuit with the first edge. 3. Select the next lowest cost edge that does not form a circuit with the previously selected edges. 4. Continue selecting the remaining lowest cost edges that do not form circuits with the previously selected edges. 5. When a spanning tree is complete, you have the minimum cost spanning tree. Example, a college campus plans to provide awnings above its sidewalks to shelter students from the rain as they walk from the parking lot and between buildings. To save money, awnings will not be placed over all of the sidewalks shown in the figure. Just enough awnings will be placed over a select number of sidewalks to ensure that students walking from building to building will be able to do so without getting wet. This is exercise 39, page 938 from Blitzer's Thinking Mathematically 7th edition textbook. A. Use a weighted graph to model the given map. Represent buildings as vertices, sidewalks as edges, and sidewalk lengths as weights. I'll begin with the classroom building. I'll use a dot, a vertex. Then I'll use a dot to denote the library. The next building, administration, denote that with a dot as well. And also the gym. Let's not forget the cafeteria. We'll note that with a vertex. And finally, we'll denote the parking lot. Now we need to connect the sidewalks, those will be our edges. From the classroom building to the library, it's 155 feet. From the classroom building to the administration, that's 80 feet. From the classroom building to the cafeteria, that's 125 feet. Between the library and the administration building, that's 115 feet. Between the library and the gym, that's 135 feet. And between the gym and the administration building, 155 feet. Between the administration and the cafeteria, it's a 55-foot walk. From the parking lot to the administration building, that's 85 feet. Between the parking lot and the cafeteria, we have 135 feet. And the distance from the parking lot to the gym is 215 feet. Now we have a graph representing this map. Part B. Use Kruskal's algorithm to find the minimum spanning tree that allows students to move between the parking lot and buildings shown without getting wet. The shortest distance is from cafeteria to the administration building. So that'll be step 1. We'll call that 55 feet. The next shortest distance appears to be between classroom building and administration. That's 80 feet. So our step 2 is 80 feet. The next shortest distance appears to be between the administration building and the parking lot. So step 3 would be 85 feet. The next shortest distance is between the library and the administration building. So step 4 is 115 feet. And continuing in that manner, we need to get to the gym. That path is 135 feet. So step 5 is 135 feet. The total length of the sidewalks that will need the awnings is 50 feet plus 80 feet plus 85 feet plus 115 feet plus 135 feet for a total of 470 feet.